So here we are again. This is Tuesday's class, March 31st, and a few announcements. I hope everyone's well, had a good weekend, got that quiz done, which is one of these announcements. So first one is free access to the book. I sent you the link in a 325 email by way of Canvas. If you don't have the book and you've been relying on my book or a book in the library or the tutoring lab, this is your chance to go get free access for the rest of the semester to that book. That way I'm going to stop taking pictures and posting pictures of homework and stuff. So please go do that. And quiz 3 is due today, 3:31, at the start of your class time. Remember, every minute late loses 5 points. So on a quiz, a couple minutes late and you've lost all the points. So make sure you get it in. A lot of you have been sending it to me as soon as you have it done, which is great. You can certainly send it to me early. The deadline is start of class time on the 31st. Spring break is next week. So this week we have class on Tuesday and then on Thursday, and then the following week is spring break, and then we come back, and that test 3 is coming up that week that we come back on Thursday the 16th on chapters 4 and 5. So just a few announcements. We're going to get started. As you know, we had some tedious graphing to do in 5.1 and 5.2. We're going to continue that and have some more tedious graphing to do in 5.3 and 5.4. So let me get rid of these announcements and then we'll start with 5.3 and 5.4. So you should have the handout for 5.3/5.4. I put the two together because the one is getting you ready to graph, and then the second section is actually doing the graphing. 5.3 and 5.4, so we've graphed in 5.1 and 5.2. We've learned how to graph a polynomial function. Nice smooth curve. We look for zeros, behavior at zeros, and behavior, all those good things to help us to graph it. Now we're going to look at graphing a rational function, which we've already talked about these rational functions. But I defined it again. A rational function is when you have a ratio or a fraction of polynomial functions, one polynomial over another one. And then you have issues with domain because you have a fraction, which means denominator can't equal 0. And we have to think about that, and that will play a part in what the graphs look like. So the first thing I did was to remind you of finding domain for rational functions. So these are just sort of review exercises in terms of finding the domain. And that first function looks like this. And we're asked to find the domain, which means we're looking for what possible values of x, what values are possible for x, which means I'm going to go look for restrictions. And we said restrictions come from x's underneath even roots like square roots, or x's in denominators. And I see x's in denominators here because it's a rational function. So that's where my issue is going to be with the domain. So I'm going to go check it out and see if there's any values that x just can't be, which means that I take this denominator and I set it equal to 0. So when I take the 3x squared plus the 5x minus the 2 and I set it equal to 0 because I'm looking for restrictions on the domain, I just need to solve this. I'm going to get 2 answers. I just have to see what they look like. Are they real? Are they imaginary? What's going on here? Do I have any real restrictions on x? So I try to solve this. I'm going to try and factor it first. There is no GCF. This is the harder big X. So 3 times -2 is -6. Add to 5. So multiply to -6 and add to 5. I would need a 6 and a -1. We'll multiply to that and add to that. But this is the harder big X. So you have 2 choices now. Either rewrite this into 3x squared plus 6x minus 2 and do grouping, or do the simplify method, which says just now take the 3x, put it over each one of these, and simplify. This would simplify into an x and a 2. The other piece does not simplify, so my factors are x plus 2 and 3x minus 1 equals 0. And again, you can always FOIL it out and make sure that it works, which it does. So I solve this, I get either x is equal to -2 or I get x is equal to positive 1/3, which means that these are the issues for the denominator being 0. So my domain restrictions, or in other words, my domain, we have different ways to write it. We can write with interval notation, we can write with set notation. I'm going to keep this real simple and just say, tell me what those restrictions on the domain are. So x can't equal -2 and x can't equal 1/3. Those are the two restrictions. So we'll just keep it kind of simple in this because we just need to know what these are in order to help us to graph these rational functions. So there's my first one in terms of domain. My second one here's my example, and I want again to find the domain. So I'm looking for restrictions on the domain. So restrictions on domain, which means, is there a square root? No. Is there a denominator that has x's in it? Yes. So I'm going to take the denominator, set it equal to 0, and solve it, and see what my restrictions on x are. I'll get 4 answers here, so be careful. You need to look at all 4 answers and then decide which ones are true restrictions on x. You could factor this. This is the difference of squares. But I know a lot of you who look at this and go, oh, I was going to throw the 1 over there. And that's fine, so I'm going to do it that way. X to the 4th equals 1. But then where you make your mistake is you take a 4th root. We don't have a property. We have not learned about a property that is a 4th root property and what its rules are. What we do know is a square root property only. Square root property says if you take the square root of both sides, you get the square root on the one side with the x, and then the other side is plus or minus the square root. It gives you 2 answers. So I'm going to do the square root property on this, not a 4th root property. There is no such thing that we learned. So I'm going to do a square root of this side, plus or minus square root of this side. Square root of x to the 4th is x squared. Square root plus or minus of 1, square root of 1 is 1, so I'm going to get either positive or -1 here. So what this really says is that I either have x squared equals 1, or I have x squared equals -1. I'm not done yet, so I've only gotten the x4th down to an x squared. Now I'm going to go do the square root property again. Square root of this side plus or minus square root of this side, square root of this side plus or minus square root of this side. So this says x is equal to plus or minus the square root of 1. Square root of 1 is 1, so plus or minus 1. Or this one says square root of x squared is x equals square root of -1 is I, so I have a plus or minus I over here. 4 answers. 1, -1, I, -I. Those are all restrictions on x. Which ones do I care about when I'm talking about domain? Only the real ones. So my domain is that x cannot equal 1, x cannot equal -1. And you could say plus or minus 1 if you wanted to. These guys aren't real, so I don't need to consider them because the domain is over real numbers only. So there's my domain for that one. And then the last one like this, and they want me again to find the domain. So I'm going to look at this. There's no square roots, but there is an x in the denominator, so I'm going to go ahead and think about the restrictions on the domain. So I'll take the denominator and I'll set it equal to 0. There's that x to the 4th again. And this time I can't factor this, at least not under our normal factoring rules. So I have really no choice here but to throw that 1 over to the other side and to recognize there are 4 answers here. This is x to the 4th. I should be getting 4 answers. So I write down x to the 4th equals -1. No 4th root property, square root property. I take the square root of this side plus or minus the square root of this side. I get x squared equals plus or minus square root of -1 is I. So this basically says either x squared is equal to I or x squared is equal to -I. These are already imaginary. I take square roots of both sides, and I've got plus or minus square root of I, plus or minus square root of negative I. These are all imaginary. I can stop now. These are all imaginary already. So when I take square roots, I'm still going to have imaginary numbers, square roots of imaginary numbers. So I don't really need to continue with this. I can conclude that the domain, since all the restrictions are imaginary, my domain is going to be all real numbers. So I could write that capital R, or interval notation, negative infinity to positive infinity. And here, so you might still think, what about that? Because there's an x down there, but think about this. If you let x be any value, 0, negative, positive, when you take it to the 4th power, if it's negative or positive, it's going to end up being positive, and then you're going to add 1 to it. Is this denominator ever going to end up being 0? Never. So that kind of helps me to feel good about what we found for the domain for that one. So just a quick little review of domain, because that's going to, again, play a part in the graphing of these rational functions. So let me get rid of this, and we'll talk about the next set of information. So the next pieces of information talk about these things called asymptotes. And we've actually seen these. I don't know, I maybe have used the word, but I'm going to formally use it now. So there's a thing called a vertical asymptote, a horizontal asymptote, and an oblique asymptote. A vertical asymptote, which I like to abbreviate with a VA. If I read what it says it's a vertical line. And remember, vertical lines are x equals a number. A vertical line representing the value that x can never be, ever. So it's like the restrictions on the function, or the restrictions on the domain. And then I wrote down as x approaches, so that arrow means the word approaches or gets closer to, as x approaches whatever that vertical asymptote number is, the y value will approach either infinity or negative infinity. So let me give you a visual of this in terms of that vertical asymptote. We actually had a perfect example back with our base functions, and that example was y equals 1 over x. And if you recall, when we graphed that, we played with the t-table, we thought about what was going on with the values, and we found ourselves graphing a piece of a curve up here in quadrant 1 that got really close to the x-axis and got really close to the y-axis, but never touched them. And then there was a piece down here in quadrant 3 that did the exact same thing. Got really close to the x-axis and really close to the y-axis, but never touched them. The fact is that if you think about the restrictions on the domain here, what value can x never be? 0, right? X can't be 0. And where is x equal to 0? That's that y-axis right there. And that actually is our vertical asymptote. So we often like to make the asymptotes dotted lines. So this actually right here, this is my vertical asymptote for y equals 1 over x. Notice as x approaches the vertical asymptote, so as x gets closer and closer to 0 on this piece up here on quadrant 1, what's the y value doing? It's getting larger and larger. It's going to positive infinity. As x gets closer on this piece, as x gets closer and closer to the vertical asymptote, what's the y value doing here? It's going down to negative infinity. So this will always hold. As x approaches a vertical asymptote from either left or right, the y value will either go to positive infinity or negative infinity, one or the other. So that's a vertical asymptote. And again, the graph will never touch it. The graph will not cross a vertical asymptote, ever. So I wrote that in bold. It said never. The x value, that value that x can never be. So horizontal asymptote I like to abbreviate with an HA. It's a horizontal line. And remember, horizontal lines are y equals a number. It's a horizontal line representing the value y can mostly never be. So horizontal asymptotes, oftentimes the graph will approach and never touch, but occasionally it will touch and cross through. Not very often, like it won't cross through 10 times, but it might cross through once or twice. You just never know with the horizontal asymptotes. But for the most part, it just approaches and doesn't touch. And notice I said that as x approaches positive or negative infinity, so as we let x get really large or really small, then the y value will actually approach that horizontal asymptote. So visually, again, y equals 1 over x is a great example to see a horizontal asymptote. The fact is when we were playing with this and figuring out the graph of this for the base function, not only did we notice the x can never be 0, we also noticed that the y value actually is never going to be 0 either. And so the x-axis, which is y equals 0, was our horizontal asymptote. So I'll do it in green and turn it into a dotted line. This is the HA. The y value is never really quite touching it. And we noticed that when we played around with our ordered pairs in the t-table. So take a look at this description again for the horizontal asymptote. As x approaches infinity, so here let's go to this piece in quadrant 1 again. As x gets bigger and bigger and bigger, that will be going this way on this graph. What's the y value doing? Getting closer and closer to 0. It's getting closer and closer to the horizontal asymptote. As x approaches negative infinity, that would be on this graph. If I let x go to negative infinity, what's the y value doing? It's getting closer and closer to that horizontal asymptote. Exactly what we're saying needs to be happening here. Again, for horizontal asymptotes, sometimes the graph can cross them. Never will the graph cross a vertical asymptote. Sometimes it will cross a horizontal asymptote. There's one other type of asymptote, and it is an oblique asymptote. And an oblique asymptote is just a non-vertical or non-horizontal line. In other words, it's going to be, a line that has a tilt that isn't vertical or isn't horizontal. I'll draw them dotted because we like to make our asymptotes dotted. That would be more like a curve. It's a line. So it's linear. It's just not vertical or horizontal. So it has a different kind of a tilt to it. Sometimes there are oblique asymptotes, and that's what this is. It represents where the graph can mostly never intersect again. So it's kind of like the HA in the sense of sometimes the graph will touch this and cross through it. Most of the time it won't. Most of the time it'll just approach it, but occasionally it will cross through. And the same idea happens here as x approaches positive or negative infinity. The y value will approach whatever that oblique asymptote is. So I drew a couple of pictures for visuals, and then we're going to talk about how to figure these things out when I don't have a visual. So this first picture I drew for a visual in this example, it looks like I have a vertical asymptote at x equal what? I heard a bunch of ones. Yes, x equals 1. I'm getting bored. I'm looking at, let's see, a couple of bikes and a ladder and a hose. So I'm pretending your faces are there and you're all nodding at me and saying, sure. So x equals 1 is the vertical asymptote. What does it look like the horizontal asymptote is on that first one? Y equals 3. Good. So there's my horizontal asymptote. And it looks like I have a little piece of a graph up here. And then I have a piece of a graph down here approaching each one of these asymptotes. I didn't approach that quite nicely, but get the idea. And I just have a bunch of questions. So I want to know what the domain is, what the range is, x-intercepts, y-intercepts, VA, HA, OA for this picture. So a visual of things initially. So domain, all possible x values. So here I am at negative infinity for x. I'm hitting this piece of the graph. So I've got all the negative values of x spoken for. 0 is spoken for. What's the x value that's not spoken for here? 1, right? And then even here, it's approaching but not quite meeting it, so 1 is an issue, and then I have all the rest of them. So it looks to me like my domain is negative infinity to 1, parenthesis, union, parenthesis 1 to infinity. In other words, everything but 1. And I'm going to write it in interval notation now. Because usually when we have a picture, we like to write the domain and range with interval notation. So x just can't be 1. That is my vertical asymptote. In terms of the range, y values, here's y equals negative infinity. Down here, it's hitting the graph. I've got all the negative y values spoken for. I keep coming up. I've got positive y values spoken for. Where do I start having, where is there a y value missing? At this horizontal asymptote, which is y equals 3, and then I pick up the rest of the y values all the way to infinity. So I think I'm missing just y equals 3. So interval notation, negative infinity to 3, parenthesis, union, parenthesis 3 to infinity. Everything but 3. That's my horizontal asymptote. In terms of x-intercepts, I look at my x-axis to see if it's hitting at all, and sure enough, it is at 0, 0, so I have an x-intercept only of 0, 0. Y-intercepts, I go and look and see where it's hitting the y-axis. Well, actually, the only place it hits the y-axis is right there as well, so my y-intercept is 0, 0, 0, 0 can be both. Vertical asymptote is the equation of the vertical line, so my vertical asymptote is not 1, it is x equals 1. Because it's the equation of the vertical line. My horizontal asymptote is the equation of the horizontal line, so y equals a number, so y equals 3. The equation of the oblique asymptote is y equals something that is linear, and there is no oblique asymptote on this picture, so I'm going to write down none. So there's that one in terms of a visual. Let me go draw this last one. One more visual, and then we'll actually go try and figure these things out without the graph to help us, and just the equation. I think I have all the same questions, so I'll leave those up. It looks like on this one, oops, I have a vertical asymptote as the y-axis, so I'll cheat here, make this dotted. And so this is my VA. And then I have an oblique asymptote, and by way of what I see where I have my dots there, it looks like I have an ordered pair 1, 1, at 2, 2, at negative 1, negative 1, at negative 2, negative 2, at 0, 0. So 1, 1, and 2, 2, and negative 1, negative 1, and negative 2, negative 2. So I can see that slope in the pattern here. So this is my oblique asymptote. And I drew my picture. Let's see, I've got a pair there. So this guy comes and approaches this asymptote, and then this asymptote, and this one approaches this guy, and this guy. So I'm going to go answer the questions now. They want to know the domain. So from left to right, here's x equals negative infinity. This guy's going to hit me. So I've got all the negative values on this graph, all the negative values of x. Where do I have an issue with an x value? Right here. The graph isn't touching either one. That's x equals what? 0. Good. And then I start hitting again and go all the way to infinity. So the only value that's not spoken for x is 0. So again, negative infinity to 0, parenthesis, union, parenthesis, 0 to infinity. Everything but 0. That looks like that's the vertical asymptote. In terms of y values, y equals negative infinity is down here, and I'm hitting all over the place. So I've got negative values of y all over the place, And I've got positive values of y all over the place. I don't see any y's missing. So I think my range is negative infinity to positive infinity. I see no issues with y values. And in fact, there is no horizontal asymptote there. So that probably is what I should have found. In terms of x-intercepts, I look at the x-axis and look to see where the graph crosses. Looks like it crosses at negative 1, 0, and it crosses at 1, 0. So negative 1, 0, and then 1, 0. Those would be my x-intercepts. Do not just put down numbers, write them as ordered pairs. My y-intercepts, I don't see the graph hitting the y-axis at all, so there are none. In terms of a vertical asymptote, there is one right here. And what would be the equation of that vertical asymptote? It's a vertical line, so it would be x equals a number, and what number is x there? 0. Horizontal asymptotes, I see no horizontal asymptotes, so there are none. Oblique asymptotes, I do see an oblique asymptote right there, and I have to come up with its equation. Well, we should be able to do this. First of all, we should be able, on this one, we should know this one as a basic function, but if we don't, look at the ordered pairs, look at the intercept and the slope. So the slope was 1 up, 1 to the right, 1 up, 1 to the right. So the slope is positive 1. So that gives me y equals positive 1x plus b. And what's b? Well, here's the y-intercept, and what's the b value? 0. So this is just y equals x. Y-intercept is 0, 0, so b is 0, and I'm all done. I don't have to put in ordered pairs and figure out the b. So there's, again, visual of graphs that are rational graphs, rational function graphs, where they have the asymptotes. The question is if we're not given the graph, and we're just given the function equation, then how do we go and actually think about trying to get it graphed and figure out its asymptotes, its vertical, horizontal, and oblique asymptotes. So that's the next goal here, is to see how to figure those out and then put it all together and get these things graphed. So I've got directions next as to how you find the vertical asymptotes, the horizontal asymptotes, and the oblique asymptotes, given the equation of the rational function. And the first thing we're going to work on is the vertical asymptotes. So number 1 is finding those vertical asymptotes. And what it says here is it says, first of all, figure out the domain, then simplify the rational equation if you can, or the rational function if you can, and then if there's any domain restrictions that are still left after simplification, those will be your vertical asymptotes. So it's kind of a two-step phase here, is that first we're going to find the domain, and then simplify, and then see what's left. See what's left of the restrictions. So, as an example, I wrote down x minus 1 over x squared plus x minus 2. So if this is my f of x, and I'm trying to think about what vertical asymptotes it has, I'm going to think about its domain, in other words, its restrictions, and then I'll go from there. So let's think about restrictions on the domain, which means denominator, x squared plus x minus 2, I'm going to set it equal to 0 and see what happens. So I do that, there's two answers here, I try to factor this. This is actually the easy big X. Multiply to negative 2, add to 1. I'd need a 2 and a negative 1 to multiply and then add. So this is x plus 2, x minus 1 equals 0, which means x is equal to negative 2 or x is equal to 1. These are my restrictions. Negative 2, positive 1 are restrictions. So that's the domain, everything except for negative 2 and 1. So domain is x can't equal -2, x can't equal 1. So now here's where some students stop and go, oh, well, that's my vertical asymptote. Those are my vertical asymptotes. Then x equals -2 would be my vertical asymptote, and x equals 1 would be my vertical asymptote. Not necessarily. So now you have to make sure that you can't simplify this, because if you can simplify this, some of these restrictions on the domain might go away, and what's left are your vertical asymptotes. So next thing I do is I ask myself, can I simplify the original, that's supposed to say simplify, the original function, which is x minus 1 over, remember this factored into x plus 2, x minus 1, and lo and behold, look at what we can do. We can simplify it, and we end up with 1 over x plus 2. So which one of these restrictions went away? The 1 went away, didn't it? So really, the only restriction we now have is x equal to -2, and that's our VA. So the VA here is x equals -2 only. So you've got to look at that simplification process to make sure that some of the restrictions don't fall away. What does that mean? So it's actually something you'll deal with more in calculus. It means that the original function does have issues with both of these values, but there's only a vertical asymptote at x equals to -2. What's really going on in the graph for this one is that there's a hole or an open circle when x is 1, but we aren't going to get into that, and our graphs aren't going to be that as complicated as that. So there's how you find the VA. You look for domain restrictions, and then you try to simplify, and either all the domain restrictions are vertical asymptotes, or some of them go away, and we only take the ones that didn't go away for a vertical asymptote. In terms of HA and OA, so let me get rid of all this, and we'll look at HA and OA now. So HA and OA kind of go together. And basically, you're going to have one or the other. And notice for each one of these, I wrote for HA, there's 2 possibilities, where you have a lower degree over a higher degree, or a same degree over a same degree. And then if it's higher over lower, it's OA. So there's basically 3 options, is that the polynomial in the numerator could be a lower degree, and the polynomial in the numerator could be a higher degree. So we're going to compare the degrees in the polynomials in the numerator and the denominator. You could have same degrees, so instead of lower over higher, you could have same degrees over each other. And then there's only one other option. It's lower over higher, same over same, or higher over lower, and that's the OA. Higher degree over lower degree. One of 3 options. Depending upon which one it is will depend upon whether it's an HA or an OA. HAs have 2 spots, OA just has the 1. How do we figure out what the actual equation is of the HA or the OA? If it's lower over higher, then I'm going to tell you that y equals 0 is the HA. So the HA will be y equals 0. Automatically right away. No other answer for that. In terms of a concrete example, I wrote down 3x plus 1 over x squared plus 2x minus 3. And I asked what the HA or OA would be. And so when I look at this, what I see is degree 1 over degree 2, lower over higher. Automatically, HA is y equals 0. Why is that? So this is a little bit of calculus, a little bit of limits, something that's called limits. Thinking just logically about what's going on here, think about letting x get bigger and bigger and bigger and bigger. What happens here, if I have a lower degree over a higher degree, the bottom is getting bigger faster than the top. And so this whole fraction is getting closer to 0. Because if the top doesn't get as large as the bottom does, so if I have 5 over 20 and then I get 6 over 100, so the bottom's getting a lot larger quicker, I'm basically approaching a value of 0 on that fraction. So we'll leave it at that. It is a concept of limits, and you'll learn a lot about those in calculus. So HA, y equals 0. Done. You've got it figured out. If it's the same degree over the same degree, then it's also a horizontal asymptote, and it is the equation y equals whatever the leading coefficient is in the top divided by the leading coefficient in the bottom. And so I wrote that down. Leading coefficient over leading coefficient will be your horizontal asymptote. I gave a concrete example of 3x plus 1 over 2x plus 5. So if this is my polynomial, my rational function, then what I notice here, degree 1 over degree 1, same degree over same degree, which means that my HA is going to be y equals, the number that y is going to equal in this case, is going to be whatever the leading coefficient is here, divided by the leading coefficient here, which would be 3 over 2. So y equals 3/2 would be my horizontal line. Y equals 1 1/2. That would be my horizontal asymptote. Why is that happening? Again, it has to do with limits. But if you kind of think about it a little bit, you can see that as I let x get bigger and bigger and bigger, adding 1 to 3 times it and adding 5 to 2 times it really isn't going to make that much of a difference. And so it's sort of like 3 times that number over 2 times that same number. What would that simplify to? It would actually simplify to 3/2. And so I can kind of see that happening even without the idea of learning limits. The last one is the oblique asymptote, and that's the last possibility where you have a higher degree over a lower degree. And the oblique asymptote comes from y equal to the quotient when you divide the denominator into the numerator and you ignore the remainder. Quotient, ignore remainder. And this is written down on your sheet of paper as well. So I gave a concrete example. I said if we have x squared plus x plus 1 and it's over x minus 2, what's going on with that one? In terms of horizontal or oblique, I see higher degree, degree 2 over degree 1, higher over lower, which means that I have to divide. I have to actually formally divide x minus 2 into x squared plus x plus 1 and get the quotient only. I don't need to worry about the remainder. So tell me about this. Do I need to do formal long division on this problem? So I'm hearing quite a few people say no. So what do I get to do on this? Synthetic division, right? Okay, so here's my next question. What do I synthetically divide by? So here we're going all the way back to chapter R. You can't forget the old chapters because we're going to use the information that we already have to build on. So what do I synthetically divide with here? So I'm hearing -2 and I'm hearing +2. Which one is it? +2. Good. It's the opposite of what's sitting there. So you're going to synthetically divide with 2. Why is it I can do synthetic division here? Again, this is linear and there is a leading coefficient of 1. So in other words, it's x plus or minus a number. That's the only thing you can synthetically divide with. What am I going to put here? These are in order. Nothing's missing. So I have a 1, a 1, and a 1. So then I bring down the 1 and I multiply, add. So 2 times 1 is 2. I add, I get 3. 2 times 3 is 6. I add and I get 7. That's my remainder. I don't even have to pay attention to that. This is what I need to pay attention to, my quotient. And what does this say? The 3 is the constant. The 1 is the x. So that means that the oblique asymptote here would be y equals x plus 3. And that would be the line that I would graph with a dotted line to show that oblique asymptote. So understanding how to find the different kinds of asymptotes. Now we've got 3 more examples where we're just going to find the asymptotes, and then we're going to flip over and do section 5.4 and actually graph some of these things. So let's go through these 3 examples just to review these concepts again, and then we'll start the graph. So they want me to find VA, HA, and OA if they exist. So to find the vertical asymptote, first I need to look at restrictions on the domain. Restrictions on the domain are coming from where the denominator, in this case, where the denominator is equal to 0. I can eyeball this one, but just so you have it in your notes, we take it, we set it equal to 0, and we solve. We're just going to get one answer, x equals 6. So in other words, restrictions are on the domain. The domain is x cannot equal 6. That's the only value that x can't be. Is that the vertical asymptote? Don't know yet until I make sure that until I can see if I can simplify this thing or not. So before I claim that that's my VA, I'm going to look at if I can simplify f of x equal to 3x plus 5 over x minus 6. So can I simplify this? In other words, can I factor anything and get maybe the x minus 6 to cancel? Well, 3x plus 5 is linear already, there's no GCF. X minus 6 is linear already, there's no GCF. So I can't simplify, so no simplification. So that means that my vertical asymptote is, don't say 6, it's a vertical line, so it's going to be x equals 6. It's what your restrictions were on the domain. So vertical asymptote, x equals 6. So now the next question is there an OA or an HA? There's not going to be both. It's one or the other, because remember they come from 3 different scenarios: higher over lower, lower over higher, or same over same. So what do I have going on here? Let me get a little more room. What do I have in terms of degrees? Linear, linear, same over same. So these are same degrees. So HA or OA, I say it's the HA. If it's same, then it's going to be y equals leading coefficient over leading coefficient, which would be 3 over 1, which would give me 3. So this was same over same, and so we got y equals 3 over 1, and that simplified to y equals 3. OA, none. Can't have both, one or the other. There's that one. Let's take a look at this next one. So vertical asymptote first, I need to look at restrictions on the domain. So restrictions on the domain. So I look at the denominator equal to 0. I can factor that. That's the easy big X. Multiply to negative 14, add to negative 5. I think I get x minus 7, x plus 2. Multiply to negative 14, add to negative 5, negative 7, positive 2. So this gives me x equals 7 or x equals negative 2. So my domain then is x can't equal 7, x can't equal negative 2. Vertical asymptotes now. Maybe they're both going to be vertical asymptotes, but I don't know yet until I try to simplify this function. So I look at, can I simplify? So I've got f of x equals, so I'm going to try and factor here. I already have the bottom factor, x minus 7, x plus 2. Can I factor the top? So, here's a good review question. X cubed plus 1, no GCF, 2 terms, sum of cubes. So sum of cubes is factorable all the way back to chapter R again. It's going to turn into a binomial and a trinomial. The binomial comes from the cube roots. Cube root of x cubed is x. Cube root of positive 1 is positive 1, or cube root of 1 is 1 and keep the same sign. What goes on in here? I take the first term here and I take it times itself. I square it, so I get x squared. The second term comes from these 2 terms multiplying and change the sign. So that's positive x, so I'm going to write down negative x. And then the last term comes from squaring this guy. So positive 1 times positive 1 is positive 1. This trinomial should always be prime. You should not be able to factor it any further. This is already linear. So now the top is factored. Can I cancel anything? Oh, that work, and I don't get to slash anything. So can I simplify it? No, it's not simplifiable. So that means that my vertical asymptote, or vertical asymptotes, are exactly what my domain restrictions were. So I'm going to write it as an equation of a vertical line. So x equals 7 is one of them, and x equals -2 is the other one. In terms of HA or OA, I need to look at degree. Degree 3, degree 2. So that's higher over lower. And higher over lower means OA. So there's none for HA. And so higher over lower means I need to divide. So can I use synthetic division on this one? No, darn. So I need to do long division. So let's see, x squared minus 5x minus 14 divided into x cubed. There's no x squared, so I'll pad it with a 0x squared. There's no x, I'll pad it with a 0x plus 1. And I'll do the formal division all the way back to chapter R again. So what times x squared gives me x cubed? You tell me x. I put the x up here and I multiply. So x times x squared is x cubed. X times a -5x is a -5x squared. X times a -14 is a -14x. All like terms should be lining up underneath like terms. I take that whole line and do what? Subtract it, so I change all of its signs. So this becomes a minus, this becomes a plus, and this becomes a plus. The first term should go away if I'm doing things right, and it does. X cubed negative x cubed gone. Second term with the x squared, 0x squared plus 5x squared gives me 5x squared. Next term, 0x plus 14x gives me 14x. And then I bring down this last term. And I can do this one more time because they're equal powers, so I can do that division. What times x squared will give me 5x squared? You tell me +5. So +5. And then I take, now the question is can I stop here? Because remember, all I'm trying to do is get the quotient. The rest of this is going to be the remainder. In other words, if I multiply this out, I get 5x squared minus 25x, 5 times -5x. 5 times -14 is -70. I take that whole line, I subtract it, so I change all the signs. This goes away. The x's become 14 plus 25, so 39x. The number becomes 1 plus 70 plus 71. But that's my remainder. I didn't need to do that. All I need is the x plus the 5. So OA is y equals x plus 5. So on this, you can stop short if you want to. So there's the second example, finding those 3 asymptotes. So let's go do this last one, and then we'll actually put this all together and try and graph some of these things. So VA, I'm looking for domain first, so restrictions on the domain. Take the denominator, set it equal to 0, and see what kind of answers I get. There are 3 answers here. So I try to, again, don't take the 1 and put it over here. You can't take cube roots. We don't have a cube root property that tells us what's going to happen. So we only have a square root property. So I'm going to try and factor this. This is difference of cubes. I'm hitting you on this one. So factor this, binomial, trinomial. Cube root of x cubed is x. Cube root of -1 is -1, or cube root of 1 is 1 is 1, and keep the sign. Take the first term times itself, so x times x squared. Multiply these two and change their sign. So -x, so I'm going to write down +x. And then square the -1, and that gives me a +1. Again, this piece should be prime. You should not be able to factor it, and we can't. So this is linear, but this is not yet, and I just said you can't factor this. So how are we going to do this? Because we should be getting 3 answers. One answer is coming from here, and 2 answers are coming from here. So this guy gives me x equals 1, right? Or I still need to think about this one. That's prime, which just means I can't factor it. It doesn't mean there aren't answers. There are 2 answers here. They might be real, they might not be real, but I need to go see what they are so I can decide what the restrictions on my domain are. So how do I do this if I can't factor it? I have 3 different ways. I can do square root property, which doesn't apply. I could do complete the square, which I don't want to, so I'm going to do the quadratic formula on this. Quadratic formula says x is equal to the opposite of b, so -1, plus or minus the square root of b squared, so 1 squared, which is 1, minus 4 times a, which is 1, times c, which is 1, all over 2 times a, which is 1, so 2 times 1 is 2. And as I start to figure this out, I have -1 plus or minus 1 minus 4 over 2. Can I stop here? Because remember, I'm looking for domain, restrictions on the domain. Domain is over all real numbers. What's going to happen here? These are imaginary. So I can stop here and say that there is only one restriction on the domain. The domain is x can't equal 1. Is that my vertical asymptote? I don't know yet until I decide if I can simplify this messy guy here. But think about this. I probably don't even need to erase this. We were able to factor this into x minus 1 times x squared plus x plus 1, right? So I'll go ahead and write it down. We were able to factor the denominator into x minus 1, x squared plus x plus 1. The numerator is just 4x squared. There's nothing I can do to factor that. Is there anything that I can cancel? No. So no simplification. So that means that, we'll use this. So that means that my VA is x equals 1. The restriction on the domain, x equals 1. HA, OA. So I look at the degrees. This is degree 2, this is degree 3. So lower over higher. Lower over higher. That means it's an HA, so there is no OA. And if it's lower over higher, what is the HA? Y equals 0. Lower over higher, the whole thing approaches 0 as we let x get bigger and bigger. And I'm all done with those examples. So just a little more practice with figuring out how to get HAs, VAs, and OAs. So now we're going to put it all together. And we're going to actually do section 5.4, which is, I'm going to give you a rational function, and you're going to graph it from beginning to end. And I'm going to insist that you use my 6 steps that I've written down on your handout when you do the homework and or when you do it for me on a test. I will always prompt you on the test with what I want you to be finding, so you don't have to memorize the 6 steps if you don't want to. So when you flip over to the other side, you'll notice I wrote down 6 steps to aid in graphing rational functions. The first step is find that domain and simplify if you can. That's so you can find the VA. Second step, okay, find the VA, find the HA, find the OA, and graph them with dotted lines, which is what we like to do. Step 3 is find and graph the y-intercept, and step 4 is find the zeros, determine the behavior of the zeros, and graph them as well. And I can't help, I need to emphasize the idea of if you're finding intercepts, y-intercepts and x-intercepts, even if they're numbers, values that you need to approximate, as long as they're real, you should be graphing them. Don't do all the work and find them for me and then not bother to put them on your graph. So I can't tell you already how many parabolas I have that you found me the y and the x-intercepts, but you didn't bother to graph them. Graph them. You'll get a more accurate graph. And 5, determine if the graph intersects an HA or an OA. Remember we said that sometimes the graph can cross a horizontal or an oblique asymptote. We have to prove whether it's going to or not. That's what step 5 is all about. And step 6 is the same as step 6 on the polynomial functions, which is let's find some ordered pairs in each section so that we can actually get a better feel for what our graph looks like. So we're going to go through these steps together on these graphs and see if I can get you feeling comfortable with these. These are tedious as well, maybe even more tedious than the polynomial ones were. I might run out of room, and so I'll have to erase a little bit to get all the work to fit on here. When I give you an XY axis like I did in number 1, it means that I am being nice. and I'm trying to set up the dimensions of the axes for you to go with the problem. So if your problem doesn't fit what I've set up, then something's wrong. So what I did on this one looks like, sometimes that can be an issue with these problems, just deciding how you're going to label your axes, and so I'm trying to be a little bit nice here. So it looks like I put 1 up here, and so -1 down here, and then these I just split up smaller. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. We'll stop there. So just trying to give you a little bit of help in terms of setting up the axes. So first thing we need to do is figure out the domain, and then from there we'll do VA, HA, and OA just like we've been practicing. So in terms of domain, restrictions on domain here, the denominator is x squared minus 16. I need to set it equal to 0 and see where I have an issue. I'm going to get 2 answers here. This is nice for the square root property. I could factor it as well. Either way, this is x squared equals 16. I take square roots, plus or minus. I get x is equal to plus or minus 4. So I've got 2 restrictions on my domain. X can't be 4, x can't be -4. So here's the next question. Can I simplify? So can I simplify x plus 3 over x plus 4? Oh, I'm going to factor it now, because x squared minus 16 factors into x plus 4x minus 4. Can't factor x plus 3. Will anything cancel? No. That means both of these restrictions are staying. So now I know my VA. So this is step 2. Figure out VA, HA, and OA. My VA, I have 2 of them. X equals 4. X equals -4. So I have 2 of those vertical asymptotes. HA or OA? Degree 1 over degree 2. So lower over higher. So that means I have an HA, not an OA. So I'll write none down for it. HA is going to be, if it's lower over higher, it's going to be y equals 0. And now I'm going to graph those. I'm going to graph them with dotted lines. What you can do, what I know some students like to do is they like to use a highlighter to graph the asymptotes, and that's perfectly fine as well. So I've got vertical asymptotes at x equals 4 and -4. So here's one vertical asymptote. Here's my other one. And then my horizontal asymptote is y equals 0, which is the x-axis. So this is where the highlighter comes in handy, because you can just kind of highlight a dotted line over it and have it show up nicely. So this is my HA. So I have 2 VAs and 1 HA, splitting my graph up into a bunch of different pieces. So that's step 2 taken care of. Step 3, find and graph the y-intercept. So the y-intercept is the ordered pair 0, something. So f of 0 is equal to 0 plus 3 over 0 squared minus 16. Again, you have to show me your work. Don't just throw out ordered pairs and don't show me where they're coming from. So I have to at least see this step so that I then know why it is that you wrote down -3/16 for your y-intercept value, for the y value of the y-intercept. I've got to see something, because otherwise I don't know what kind of a calculator you're using, and the graphing calculators are amazing. So you've got to show me work so that I know where things are coming from. And this is awkward to graph, so I'm going to approximate the -3/16 in my calculator, and that is approximately equal to, I'll put it underneath, I'm going to round it to the nearest tenth, so -0.2. So I've got the ordered pair 0, -0.2. So you can see why I brought -1 all the way down here. So there's 0.5, so it's maybe right around there is my 0, -0.2. So this is my 0, -3/16. Next step, so now I've got one ordered pair and a bunch of asymptotes. Next step, step 4 says, okay, find the zeros now and determine the behavior at the zeros. Okay, this is no different than what we did on the polynomial functions. So finding the zeros means that we are finding the x-intercepts. In other words, we are finding where y is equal to 0. Behavior at the zeros, so what was that? All had to do with multiplicity. If it's multiplicity 1, then the behavior at the 0 is that it crosses through with no wiggle, no change in the curvature. If it is multiplicity even, so 2, 4, 6, 8, 10, etc., then it's going to bounce. It's not going to actually cross through. It's going to come down, touch, and then bounce off. And if it is multiplicity odd bigger than 1, so like 3, 5, 7, 9, etc., then it's going to cross through, but with a wiggle, so the concavity is going to change as it crosses through. No different or new rules. So finding the zeros means let y be 0. So that means I'm trying to solve 0 equals x plus 3 over x squared minus 16. So there is a little hint on this number, but let's just formally solve this and then you'll see why I wrote down the hint. For this to equal 0, it's a fraction, and I want to clear the fraction, so I'll multiply both sides by the LCD, which is just x squared minus 16. So when I take both sides times x squared minus 16, what happens here? Anything times 0 is still 0. These cancel, which was my goal, and I'm left with just x plus 3 equals 0, and that was my hint. When you have a fraction equal to 0, what part of the fraction is going to have to be 0 is the numerator, right? 0 over some other number will give you 0. So the fact is that you could do it formally or recognize that it's just the numerator goes to 0, and that's what that little hint says. And so this gives me one answer. X is equal to negative 3. So in other words, my 0 is negative 3. Multiplicity 1. Negative 3 multiplicity 1. It's only there once. It was linear. Which means that the behavior at the ordered pair negative 3, 0, and we got one x-intercept, is what? Multiplicity 1, it crosses through, no wiggle. Through, no wiggle. So I'm going to go graph my x-intercept, which is negative 3, 0, which is right there. Notice it's on the HA, so it looks to me like we are going to cross the HA on this particular problem. So my x-intercept, or my 0, is negative 3, 0, and it's through with no wiggle, which means that when I cross through here, I'm either going to be crossing through maybe like this. So why am I saying that? Well, I'm respecting this VA. The fact is the vertical asymptote here, I can't go this way because then I'll cross through it. You never ever cross through a vertical asymptote. So I could come and approach it in this direction, or I could come and approach it in this direction and then have no wiggle going like that. But think about which one makes more sense, because see that ordered pair right there? If it's the solid one that I drew with no wiggle, approaching the vertical asymptote, crossing through here, then to get to this point, what am I going to have to do? I'm going to have to come back down. I'm going to hit the x-axis again, and how many x-intercepts or how many zeros did I find? Just the one, just here. I'm not going to hit again. So there's no way that this one can work from what I'm seeing. So I'm going to get rid of it. I think that this guy is going to come like this, approach this vertical asymptote, come through here with no wiggle, and come down here. And then I'm not sure what it's going to do, although I'm pretty sure it's not going to come back up like this, because again, I'm hitting the x-axis again, and we found only one x-intercept, so I'm thinking it's going to come down and probably go like this. So I kind of think I know what the middle piece is doing. What I don't know is what's going on over here yet. So that was step 4. It's all done. I determined the zeros and the behavior. So step 5 says, determine if the graph intersects the HA or the OA. So that's the next step here. I'm going to erase this little piece. So step 5 is, do they intersect? So for two things to intersect, it means that we're going to set them equal to each other. In other words, this says y equals x plus 3 over x squared minus 16. This says y equals 0. I'm trying to see where this graph intersects with this HA, if it does. So I'm going to set the two pieces equal to each other because they're both y, so I'll substitute and say this equals this. So for intersection, the comment there says that you set fx equal to the HA or the OA. So I'm going to take the x plus 3 over x squared minus 16, and I'm going to set it equal to this y value of the HA, which is 0. But guess what? We just did this. Look, it's a repeat, and it has a little bit to do with the fact that the HA was y equals 0, and that happens to be where the zeros of the function are. So I've done this already. This gives me x equals negative 3. So I did this already, did the work. I don't want to get in here, did work already. Don't need to do it again. If you've already done it, you don't need to repeat it. So yes, it does intersect. It intersects at when x is negative 3, the y value is going to be 0. So guess what this is proving to me? This is proving to me that the only time this graph is going to hit the HA is right there and there only, which we kind of already knew because of the zeros, and it has to do again with the fact that the HA is on the x-axis. So we've now proven that this is the only place where it intersects. So as I draw this, I'm never again going to touch the HA. Never ever touch the VAs, and I'm never again going to touch the HA. The only place I'm touching is right here. So now I'm absolutely certain that this is going to come through here and approach the VA, come through here, hit my y-intercept, and it's not going to come back up because I can't cross here again. So I'm thinking it's going to come down like this. I'll do it light because I'm going to get some ordered pairs now to try and figure things out. So that's what step I'm at. I'm at step number 6 because the only thing I think I know for certain is what's going on in here between these two vertical asymptotes. What I don't know, have any idea, is what's on this side of the vertical asymptote and what's on this side. And that's where step 6 comes in handy. It gets me some ordered pairs. So I'm going to go try and find, so it says find an ordered pair in each section or interval determined by the VAs to get a more accurate sketch of the graph. If there was an OA, I would also use it to get me some ordered pairs. The more the merrier. The fact that there's two vertical asymptotes here means I really only need to pick one value less than the -4, a value in between here that I haven't already found, and then something bigger than 4. If you want to get more than that, I have no problem with that. Just be careful with your time. So in terms of ordered pairs, I'm going to go look for what happens when x is -5. So in other words, to the left of -4, so I can see where the graph is here. I'm going to go look and see what happens. So I already have -3. I could do -2 or -1, but those aren't as necessary in my mind because I know it has to come down to here as over here. I kind of want to make sure that I know what's happening over here and that it really isn't going to cross again. So I'm going to go pick 1, 2, or 3, and I think I'll get 3 just so I can make perfectly sure that it's approaching the vertical asymptote. So I'm going to get when x is 3. And then something beyond 4, so I'll grab 5. And I'll get those ordered pairs, and I will graph them, and I'll fill in the rest of this graph. So I need to go figure out f of -5. So that's going to be -5 plus 3 over -5 squared minus 16. That gives me -2 over, that's 25 minus 16, which is 9. So again, -2/9. So let's approximate that. So I put that into my calculator because I want to graph this. And -2/9 is approximately equal to, if I round it to 1 decimal point again, approximately equal to -0.2. So I've got -5, -0.2. So down in here again, here's -5, -2/9 that's really all I need, because I already know that the piece of the curve that's here is going to approach the HA and not touch it, or cross it and approach the VA and not cross it or touch it. So I can just draw a smooth curve that approaches each one of those asymptotes, and there's that piece. There's nothing up here. The fact is I took an ordered x value over here and it put me down here. So every x value I pick over here is going to put me down here because I can't cross any of the asymptotes. So now I'm going to go do the 3 and hopefully it'll be down here somewhere. So I put in as a 3, so I'll do that work over here because I'm running out of room. So f of 3 is 3 plus 3 over 3 squared minus 16. That gives me 6 over 9 minus 16, which is negative 7. So I get 3 negative 6/7. And again, if I approximate that in my calculator, that was about a negative 0.9 if I take it to one decimal place. That's perfect. So here's 3, here's 3, here's negative 0.9 right around here. So that's exactly what I thought should be happening. So my curve is going to just sort of snakes down. Looks like y equals negative x cubed almost, huh? That vertical snake snakes down and gets closer to this. Now I just have to go see where this piece is. It's either going to be up here or down here. Don't know yet. I'm going to go put in f of 5 and see. So f of 5 is 5 plus 3 over 5 squared minus 16, which is 8 over 25 minus 16, which is 9. And then I approximate that. So this is 5 8/9 for my listed ordered pair, but I'm going to go approximate it so that I can graph it nicer, and that's approximately equal to 0.9 positive. So 5.9, so that's way up here. So now I'm a little uncomfortable. Not too much. I figure it's going to approach and then it's just going to come down rapidly and approach here. So I might go get one more value over here just to make sure that it's down here somewhere. So maybe I didn't pick far enough over. So I'm going to go grab f of 7 just for the heck of it. So I've got 7 plus 3 over 7 squared plus minus 16, which is 10 over 49 minus 16. And 49 minus 16 is what, 33? So 10 over 33, so I did an extra one here, 7, 10 over 33, which if I simplify that, that's about, 0.3, right? So that's approximately 0.3. So that makes me feel a little bit better. So 4, 5, 6, 7.3 is maybe right around here. So now it is exactly what I thought was happening. So it's curving down and then approaching each one of these asymptotes. Did I have to do that last one? No, but again, there's nothing stopping you from getting more ordered pairs than what have been asked for. And so I have a pretty good representation of what the graph of that rational function looks like. Tedious, very, very tedious. And I forgot to, so I didn't label this guy. I'm not going to mark off if you don't label them as long as you have them written down here. So there's 3 negative 6/7, so this guy was the 5 8/9. And then I added an extra one right there, which was the 7, 10 over 33. Again, as long as you have them written down formally for me in the spot that I give you on the test, you're okay. You don't need to label them there, but I thought I would in the graph. So there's the first one. The second one, we're just going to do VA, HA, and OA for some more practice, and then we'll graph that last one for our final practice with graphing these things. So this next one, we're not going to graph, we're just going to figure out the asymptotes. So in terms of VA, HA, and OA, to figure out what the VA vertical asymptotes are, I need to look at restrictions on domain. So restrictions on domain, I take the denominator, I set it equal to 0, 2 answers. I'm going to try and factor. It looks like the easy big X, -6, -1. So multiply to -6, -3 and a 2, add the -1. So this is x minus 3, x plus 2 equals 0, which means x equals 3 or x equals -2 are my restrictions on that domain. X can't be 3 and x can't be -2. Are those my VAs? I don't know yet until I try to simplify. So can I simplify the function 6x squared over this factored into x minus 3, x plus 2? Can I simplify that? No. So that means that my VAs don't change. My vertical asymptotes are going to be x equals 3 and x equals -2. My HA or my OA, I look at degrees. This is degree 2, this is degree 2. Same over same, that means it's an HA, that means there's no OA. Same over same means that my HA is going to be y equals leading coefficient over leading coefficient, 6 over 1, which is 6. So this is coming from same over same. So we do y equals 6 over 1, the leading coefficients, and we simplify it, so y is equal to 6. So there's that one, nice and quickly done. Those hopefully are going to get so they don't take very long at this point. The hard part is getting the graph actually graphed. I can see the red is really hard to erase on this board. So I'm going to get my exercise here. Since I don't seem to be able to get it anyway else, because I know some of you know I swim a mile a day, and I mix up the strokes, and it's hard to do that when your gym is closed, and it's hard to do that when your pool is too cold and the ocean water is too cold. So I'm getting my exercise erasing this board apparently. And in the meantime, I forgot to erase this piece. So let me get this and we'll go do number 3. Okay, so last one, they want me to graph and use the steps. So step 1 is find the domain, restrictions on the domain, so that we can then make a conclusion for VA, OA, and HA. So restrictions on the domain, I take the denominator and I set it equal to 0. This one I could probably just eyeball, x equals 2. So that's the restrictions on the domain, x cannot equal 2. Is that going to be my vertical asymptote? I have to go see if I can simplify this. So can I simplify f of x equals x squared plus 1 over x minus 2? Well, I can't factor x minus 2. Can I factor x squared plus 1? Sum of 2 squares. It's not factorable from our viewpoint of factoring rules. So nothing will cancel. So that means the restrictions are all going to stay on the domain. So that means my VA, so step 2, VA, HA, OA, my vertical asymptote is x equals 2. Horizontal or oblique, degree 2 over degree 1, so higher over lower. So that means there is no horizontal asymptote this time. This time it's an oblique asymptote. How do I find that? I need to formally divide. So tell me about this one. Do I have to formally do this along division, or can I use synthetic division? I'm hoping you're all saying synthetic, synthetic. And what is it that I'm going to divide with when I do synthetic division? I'm going to divide with positive 2. Good. And what am I going to write down here? Am I going to write down 1, 1? So I see some of you shaking your head yes, and some of you shaking your head no. I can see all things. Which is it? There's a missing term, right? So it's going to be 1, 0, 1. There is no x. X squared, x, and then the constant. Bring down the 1, multiply, I get 2, add, I get 2, multiply, I get 4, add, I get 5. That's my remainder. I don't even have to worry about it. My OA is y equals constant x, so x plus 2. So now I'm ready to start graphing these vertical asymptotes and oblique asymptotes. And notice on this one, I just gave you a normal XY axis with all the squares marked in, which is always nice when that happens because we can use our little boxes, our little corners of our squares on the graph paper. So we've got two asymptotes here. X equals 2, so I'll do those in red. So I've got 10 either way. So x equals 2 is the vertical asymptote. And my oblique asymptote, now I need to be really careful. You know, the horizontal and vertical lines are easy to draw. The oblique one, you need to be very accurate when you draw it. So it's not good enough just to get a couple of points. So something I've been emphasizing when we've been graphing lines is to fill up the entire graph paper, the 10 by 10, and get it accurate. So y equals x plus 2 means that my y-intercept is 2 and my slope is 1. So it's 1 to 1, so 1 up, 1 to the right, 1 more up, 1 more to the right, 1 more up, 1 more to the right, 1 up, 1 to the right. And you can do this very nicely on your graph paper. It's a little harder for me on here, but I'll try to get it reasonably accurate. 1 down, 1 to the left, 1 more down, 1 to the left, 1 more down, 1 to the left. So fill in all the little marks on each corner of the square so that you get a really straight line, which is what they should be. But do it with dots. Don't fill it in as an actual full line. Just do it as a dotted line because it's actually just a asymptote. So I'm going to fill these in with a dotted line. And again, do it the whole way. So that way it's very, very accurate. So this is my oblique asymptote. So now the next step I'm going to get is the y-intercept. So step 3 is the y-intercept, which is the ordered pair 0, comma something. So f of 0 is equal to 0 squared plus 1 over 0 minus 2, and that's equal to negative 1/2. 1 over negative 2, which is negative 1/2. So negative 0.5. So 0, negative 0.5 is right there. So there's my y-intercept, 0, negative 1/2. I'm going to go get my x-intercepts now, or my zeros. So the zeros are the x-intercepts, which means something, comma 0. So I'm going to set the y value as 0 equals x squared plus 1 over x minus 2. And again, you could formally do this and multiply both sides by x minus 2, right? But honestly, what's going on here, anything times 0 is still 0. These cancel and you're left with the numerator equal to 0. That's the only way a fraction is going to equal 0 anyway. So this is what I need to solve. And this says that x squared is equal to negative 1. So I'm going to get two answers, but what are they both going to be? Imaginary, right? Plus or minus I. X is plus or minus I. So my x-intercepts are, I'll do it in one shot here. I comma 0 or negative I comma 0. Can I graph those? These are imaginary. Can't graph them. So what is that telling me? It's telling me that there are no x-intercepts at all. So in other words, this graph is never going to cross. We got extra piece of information here. This graph is never going to cross the x-axis. So I have this point, these asymptotes. So from this point, which way could I start to graph? Can I take it and go up like this? No way. Or up like this? No way. So in my mind, this must be going like this and like this, approaching the vertical asymptote. The only thing I don't really know is it could approach this and actually cross through it. We haven't figured that out yet. Or maybe it's just going to approach it and never cross through it. That's actually my next step, I believe. So step 5 is determine if the graph intersects or not. So I'm going to do that next. I'm going to go erase this piece here and look at whether it intersects or not. So I'll leave those up. So step number 5, intersect. So again, the intersection means set this says y equals this, and my oblique asymptote said y equals x plus 2. I'm going to set the two equal to each other. So in other words, x squared plus 1 over x minus 2, this y has to equal the y of the oblique asymptote, which was y equals x plus 2. So this y has to equal the other y. And I formally solve this. So how do I solve this? Now I do need to multiply both sides by the LCD, which would just be the x minus 2. So I take the left side times x minus 2 and the right side times x minus 2. These cancel. I get x squared plus 1 equals. These, nothing cancels, so I have to multiply it out. So I'm going to FOIL this, and these are conjugates, so what's going to happen? I'm going to get x squared. What's going to happen to the middle term? Negative 2x plus 2x is going to go away. Positive 2 times negative 2 is a negative 4. So this is what I now have. What kind of an equation is this? It looks quadratic, but what's going to happen when I try and get all the x squared on one side? They're going to go away. And so now I have 1 equals negative 4. So what happened here? The variable dropped out, so variable's gone. And I have a very false statement, right? What does that mean? If the variable is gone and you have a false statement, that means that there is no solution. So this gave me no solution, which means that there is no intersection between the two. So no intersection, which means the graph never crosses the OA. In this particular case, my graph is not going to cross the OA. I got no place where it intersects. I got no solution to that. And as a result, I now know that it doesn't cross the OA, it doesn't cross the VA, and I also know it's not going to touch the x-axis either because I had no real x-intercepts. So I have lots of pieces of information, and now I'm going to go get some ordered pairs and see if I can fill this in. What I already can tell you is that this piece right here is going to have to go like this and approach here, and it's going to have to go like this and approach here. I know that for a fact, just by all the pieces of information I have. Can't touch this, it can't touch this, and it can't cross the x-axis. This is the only way I can go. But I'm going to get ordered pairs to substantiate that. What I don't know is if there's anything going on here or over here. So that's when my ordered pairs are going to come in handy. So this is step 6. I'm going to go get some ordered pairs. I let the OA dictate a little bit to me as well. So in other words, the OA is passing through at -2. So I'm going to go grab an x value over here just to make sure that it's down here. So maybe I'll grab, what one did I grab? I grabbed -5, but you could grab anything smaller than that, smaller than this -2, but I wanted to go over a little bit so I could make sure. So I'm going to grab -5 for an x value. I'm going to go grab an x value in between the OA and the VA. I already have 0. So maybe I'll grab -1 or even -2, or I could grab 1. So I have a bunch of choices here. You can grab all of them if you want. I think I'm going to do 1 just to make sure, because there's just in my mind no other way for this, and I'm going to get a point over here anyway. So I'm going to go grab 1 to substantiate that this also goes down. And like I said, you can always do more than what I'm doing. And then I'm going to go grab an ordered pair past this 2. So I grab 3, and I might grab more just to make sure, but we'll see. So I'm going to go plug these in. So f of -5 is equal to -5 squared plus 1 over -5 minus 2. That gives me 25 plus 1, which is 26 over -7. So this is -26/7, which again I'm going to approximate. And when I approximated that, I got approximately -3.7. So I've got -5, -3.7, 1, 2, 3, 4, 5, 1, 2, 3. I just want to make sure, which it is, that it's underneath my dotted line, and you can tell that better if you graphed it accurately on your graph paper. So that looks really good. It's approaching, never quite touching, just getting closer and closer. I'm going to go grab 1 now and make sure that it's down here as well. So when I do f of 1, I get 1 squared plus 1 over 1 minus 2. That's 1 plus 1, which is 2. That's negative 1, so that gives me negative 2. That one was nice. I didn't have to approximate it. So 1, negative 2, there it is. I didn't quite, but almost. 1, negative 2 is right around there. So there it comes like that. So here's my 1, negative 2. Here's the 0, negative 1/2. Here's the negative 5, negative 26 over 7. So I have this piece pretty well figured out in here. The only thing I don't know, so I know everything from negative 2 to the left. It's just right in here. Even if you pick negative 10, it would be down here. I've already kind of shown that with the negative 5 choice. I need to pick something bigger than 2, so I chose 3. So I'll go put that in. So f of 3 is equal to 3 squared plus 1 over 3 minus 2. That gives me 9 plus 1, which is 10 over 1. So that's just 10. That was nice. So 310. So 310 is right here. So what is this telling me? This is basically telling me that there's going to be a curve in here that's going to, I don't know how far it's going to come down, but it's going to come and approach each one of these, because again, I know it can't cross any of them. It might be nice to get one more ordered pair, so maybe I should pick 5 and make sure, just kind of see if it comes down at all or not. So just for accuracy, if nothing else, I'm going to also take 5 and take a look at it. So f of 5 is 5 squared plus 1 over 5 minus 2. That's 26 over 3. And when I approximate 26 over 3, did I do this one? No. So I get 8 2/3. So 8.7 approximately. So 26 thirds. 8.6, so when it's 5, 1, 2, 3, 4, 5, it's 8.6, so it comes down a little bit. Okay, so that makes me feel a little bit better. So I've got a piece in here that then is going to come and approach each one of those asymptotes and never quite touch them. So there's my graph of that one. Again, tedious, a lot of thinking, and a lot of strategic planning on what points I want to pick. Sometimes the more the merrier, but you have to abide by your time limits and how many points you want to get, but you have to get at least one representative one in each piece so that you know what's going on. So that's 5.3 and 5.4. We're actually going to start 5.5. We got a little bit more time here. So we're going to go take a look at 5.5. I'm going to go erase all this stuff. That was fun, huh? I should tell you, this is the second time I did this lesson. Of course, the most tedious one, because the first time I did it, I cut off the top 6 inches of my board on my video. Somehow I must have moved my tripod trying to get rid of the shadows of the sunlight coming into my garage and didn't realize it. So I had to do that all over again. I thought you would find that amusing. Live and learn. So let's take a look at 5.5. 5.5 is polynomial and rational inequalities. So you know we did the quadratic equations, we graphed quadratics, which were parabolas, and then we did quadratic inequalities. And we said we could either look at the visual and figure it out, or if we don't have a visual and we don't want to have to graph the parabola, we could do the idea of getting our critical values and doing test points. Well, guess what? For polynomial and rational inequalities, it's the same ideas. If we have a visual, then we'll look at the visual and figure it out. If we don't, we sure don't want to have to graph these if we can get away with it, because they're very complicated to graph. So as a result, there will be a really nice way to get critical values and do it the way we did the quadratic inequalities. So what I do first is, again, I give you a visual. We're talking about polynomial inequalities and rational inequalities. We'll look at the polynomial inequalities first. So you'll notice that for that polynomial inequality, I drew a picture, a visual. And so I drew, let's see, what did I draw here? So I drew a polynomial function that looks like this. So this is polynomial, a nice smooth curve with then behavior and zeros and behavior at the zeros, etc. And I asked, where is f of x greater than 0? And where is f of x less than 0? So if I have the visual, I can take a look at this and figure out this is asking where is y greater than 0. So where are the y values greater than 0 here? Well, I see y values greater than 0 here on this piece. And I see y values greater than 0 here on this piece. So in terms of writing that in interval notation, over the x values from left to right, this is x equals -2, so I'm starting at -2, but not including it because I want y to be strictly greater than 0, not equal to 0. And it goes all the way until x is 1, so -2 to 1, don't include it. And then I skip over some pieces, so union, and then I start again at x equal to 3, not including it, and I go all the way to infinity. So looking at this picture, I can decide where the y values are greater than 0. Looking at this picture, I can also decide where the y values are less than 0. So y values less than 0 would be down here, and this piece right here has y values that are less or smaller than 0. So describing that with interval notation from left to right, so over x values, this would be an x value of -infinity until I get to the x value of -2. Don't include it because again we don't want the y to be 0. And then this piece, so then I skip pieces, so I put in a union. This piece starts at x equal to 1, don't include it. And I go to x equals 3, don't include it. So here's where the y values are greater than 0, here's where the y values are less than 0, looking at the picture or the graph of the polynomial function. And again, if I put all these together, I should kind of get from -infinity to infinity, except for the actual zeros. So -infinity to -2, -2 to 1, 1 to 3, 3 to infinity. So you can kind of see the pattern there. So there's the the polynomial inequality, the picture. So what if, we're not going to look at the rational inequality picture yet, we're just going to do the polynomial inequalities. I have 2 examples of polynomial inequalities where I don't have pictures down below. And the question is how do I solve them if I don't want to have to graph them? Because if I can get away with not graphing them, then I want to get away with not graphing them. So the process is exactly the same as it was for the quadratic inequalities. So if you look, there are 3 steps to solve a polynomial inequality algebraically. Pretend it's an equation and solve it. Those values are the critical values only. We'll split the number line into intervals. We'll take test points, number 3, plug them in and determine which intervals are part of the solution and then express it with interval notation. So the exact same directions. So this shouldn't be hopefully too hard. We're going to go do these 2 examples and then I'll stop. So this first one is an inequality and it is a polynomial inequality because this is a polynomial. It's not rational, it's not quadratic either. Notice the power is 3. So I'm going to, since it's an inequality, I'm going to pretend in order to get the CVs. So I want to get critical values, so I will pretend that it says x cubed plus 8x squared is equal to 0. And I'll solve that just to get the critical values. How do I solve this? Well, we learned way back in chapter R, I think, or maybe chapter 1, I can't quite remember, but way back when, that even if it's not quadratic, you can use the zero factor property to solve a higher powered polynomial. It has to have 0 over here, which it does. So I'm going to try and factor it. There is a GCF of x squared. I will pull it out and get x plus 8 equals 0. Again, how many answers should I be getting? 3. It might not all be distinct, but I should get 3 answers. This one plays a part in my answers, And how many answers am I getting from this one? Are actually 2. It's x squared equals 0, so x equals plus or minus the square root of 0. So x is 0, it's just there twice. So this is x equals 0, in other words, multiplicity 2, which isn't going to matter in this, but here's one of my critical values. And my other critical value is -8. So these are CVs only. Okay, they do not, you don't get to put a less than with them or anything yet. You have to put these on a number line and do test points. So I've got a -8 and I've got a 0. So I need 3 sections of test points. So my first test point, I'll grab -9, put it in the original, so -9 cubed plus 8 times -9 squared, is that less than 0? So when I cube this out and put it in my calculator, I didn't bother to write down the stages. So -9 cubed is going to be a -729, and then 8 times a -9 squared is going to be a positive 8 times 81, so 648. And when I added those two, I got -81. And is that less than 0? And sure enough, yes it is. So this piece works. Then I did a test point in between -8 and 0, so I grabbed -1 as an easy one to do. And so I had -1 cubed plus 8 times -1 squared. Is that less than 0? So that's -1. This stays plus 8. Is that less than 0? And you tell me no, that is not less than 0. Because that gives me 7, and 7's not less than 0. And then I did a test point in this piece, which I grabbed 1, because again, that's easy to do. So 1 cubed plus 8 times 1 squared, is that less than 0? This is 1 plus 8, is that less than 0? That's 9, that's not less than 0 either. So that piece didn't work. So my answer is sitting right here on my number line. So in interval notation, the solution to this polynomial inequality is going to be only this piece, which is -infinity to -8, parenthesis or bracket, so strictly less than, so I'm not going to include the -8, so -infinity to -8 would be my solution to that one. All without a graph. Oh gosh, we'd still be graphing it if we had a graph at first. So that's nice. Let's do one more and then I'll stop. So this last polynomial inequality says this, and they want me to solve this. It's polynomial, it's an inequality, so I'm going to pretend it's an equation to get my critical values. So critical values, pretend that this says x cubed plus 2x squared minus 3x is equal to 0. I'm going to try to factor, so I see I can pull out an x and get x squared plus 2x minus 3 equals 0. I'm going to keep trying to factor this because it's not linear yet. And this is the easy big X. Multiply to -3, add to 2, so 3, -1. So this is x, x plus 3, x minus 1 equals 0. So how many answers should I be getting? 3. This x does play a part. This says x equals 0, or this says x is -3, or this says x is 1. These are critical values only, okay? These are not solutions yet. They're just critical values. They're dividing my number line up into pieces that I'm going to then test. In other words, don't try to make some conclusion with that greater than. X is not greater than 0 and at the same time greater than -3 and at the same time greater than 1. That doesn't work. There's a lot of logistics behind that if you're going to do it that way. So these are just critical values. I'm going to put them on my number line in order. So I've got a -3 and then a 0 and then a 1. I'm going to spread them apart so they're not nicely, I'm not counting the little hash marks. I'm just spreading them equally apart, and I'm just thinking about picking a test point in between each one. So actually in this one I have 2, 3, 4 test points that I have to do. So test point smaller than -3, so I'll grab -4. So -4 cubed plus 2 times -4 squared minus 3 times -4. Is that greater than 0? So this is -64. This is positive 32. This is positive 12. Is that greater than 0? So that gives me negative 32 plus 12. Is that greater than 0? No, that's going to be negative, right? So this is a no. So now I'm going to pick something in between negative 3 and 0. So I'll do a test point of negative 1 is a nice one. So negative 1 cubed plus 2 times negative 1 squared minus 3 times negative 1. Is that greater than 0? So that's negative 1. This is positive 2. This is positive 3. And is that greater than 0? That sure is. 5 and a negative 1, 4. 4 is greater than 0. So this one works. And then I'm going to go do a test point between, oh, this is mean. I'm going to do a test point between 0 and 1. So I'm going to get out my calculator. I'm going to do a test point of 0.5. I promise on a test I'm not going to do that to you. The test is already long enough. So test point of 0.5. So let's see, I've got 0.5 cubed plus 2 times 0.5 squared minus 3 times 0.5. Is that greater than 0? And when I put that into my calculator, I got negative 0.875 over here. And is that greater than 0? And I said, no, it's not. And then I did one more test point over here bigger than 1, so I grabbed test point of 2. So I've got 2 cubed plus 2 times 2 squared minus 3 times 2. Is that greater than 0? That's 8 plus another 8 minus 6 greater than 0. 16 minus 6 is 10, so yes, 10 is greater than 0. So now I've got my answer here in interval notation. I never had to draw a graph of this. Doesn't start until here at the negative 3. Do I put a bracket or a parenthesis on that negative 3? I put a parenthesis on it because it's strictly greater than, not less than, so, or not equal to. So parenthesis negative 3 until I get to 0, parenthesis. None of these are included. Then I skip over that x, so I do a union, and then I pick up another answer here, parenthesis 1 to infinity. So those are the values for x that will work in this problem. So we're going to stop there. We still have to finish 5 and do the rational inequalities and how we do them. It will be very similar. There'll just be one extra little piece of information to do. So let's see. I have one more thing, which is that I rolled the die before I did this video. And for chapter 3's homework, which was on the last test, which I said I might do for extra credit in terms of collecting one of those assignments. So I rolled the die for chapter 3, I decided, instead of chapter 2. And I rolled a 1. So that means 3.1. So if you want to, for extra credit, you can take a picture of the homework that you did for 3.1 and send it to me by way of an attachment in Canvas. And today's Tuesday the 31st, so it would be due no later. The deadline would be Thursday, April 2nd, so Thursday's class, at the beginning of your class time, no later than the start of your class time. So 3.1, if you want, for extra credit, take good pictures of it, however many pictures it takes, and send them to me, and you'll get extra credit for it. So have a good rest of your day. Hopefully this one worked, and I'll see you on Thursday, and we'll finish chapter 5. See you later.